This video is about work, energy and power, and there are a number of formulae that you need to know and you will need to practice. This video simply goes through the formulae and explains what they are. So you should make a note of these formulae so that when it comes to class time we can practice applying them to situations. So the first formula is simply that the work done by a force is the force times the distance. So if we have a box being pulled across a horizontal floor by a force of magnitude 15 newtons, and if it goes a total of 7 meters, then the work done is simply 15 times 7, which is 105, and the units are joules. So J stands for joules. Now if a particle is moved vertically, then the work is done against gravity. So using the fact that work equals force times distance and the force equals mg, then the work done against gravity is the force times the distance. Well, its force is mgh. So if we have a situation where a bricklayer is raising a load of bricks of total mass 30 kilograms and it's at a constant speed, and we need to find the work done when the bricks are raised a distance of 7 meters, then T equals 30g because it's a constant speed. So the work done is mgh because I said it was 7 meters, so that's 210g, which works out to be 2,100 joules to 2 sig figs. So this next one is a little bit obvious, I hope. If the force is acting at an angle, so for example we've got 27 newtons acting at 25 degrees, then the work done is the component of force in the direction of motion. So if this is being pulled along horizontally, so it's 27 cos 25 multiplied by the distance moved in that direction. So if it's moved 15 meters in that direction, it's multiplied by 15, and that works out to be 370 joules to 2 sig figs. Now, two concepts of energy to consider. The first one is kinetic energy, and that's equal to half mv squared, where m is obviously the mass and v is the velocity of the particle. So that's the energy that it possesses while it's moving. Potential energy is the energy which a particle has depending on where it is. So if a particle is at a certain height, then its potential energy is equal to mgh. So we need to know about kinetic energy and potential energy using these formulae. Now if we consider Newton's second equation, force is mass times acceleration, and we also consider the fact that v squared equals u squared plus 2as, what we can now do is rearrange this equation to write a equals v squared minus u squared over 2 times s. So combining those, we now get f equals m v squared minus u squared over 2s. Let's move the s up to the other side, so that's force times distance. We've got a 2 at the bottom, so that's a half, so it's a half mv squared minus a half mu squared. So this explains why the work done, that's force times distance, is the change in the kinetic energy. So this equation here is very important. Work done, force times distance, is the change in the kinetic energy. Kinetic energy is half m times the speed squared. So if a particle is moving, initially it had this amount of kinetic energy, and after a certain time it's got that amount of kinetic energy, then we've got that formula. So the generic term for kinetic and potential energy is mechanical energy, and so we get this principle, which is when there's no external forces acting on the particle, less gravity, then the sum of the kinetic energy and potential energy remains constant. So this is the principle of conservation of mechanical energy. Mechanical energy is the overall name for potential or kinetic energy. Conservation means it stays the same. So because of that, the mechanical energy stays the same, so the sum of kinetic plus potential energy remains constant. So let's consider that in more detail. Suppose we've got a particle which is sliding down a smooth plane which is inclined at 30 degrees to the horizontal. Suppose the particle starts at rest, and after a certain time it's got a speed of 6 meters per second. What is the distance that the particle travels before it gets to 6 meters per second? Now there's one further force that I've not shown here, and that's the reaction, the normal reaction to the plane. And bear in mind that because the particle does not travel in this direction, just travels down here, doesn't travel in that direction, then the R does no work, because work is force times distance travelled in the direction of the force. So the particle isn't travelling in the direction of the force, so the force does no work. So let's think about the decrease. Let's think about the decrease in potential energy. That's going to be mgh. So m is 0.5, g is g, and h we can calculate by thinking about the distance that it travels. So let's say it travels a total of x. That's what we're trying to find. We're trying to find the distance that it travels. So if we think about this little triangle here, there's h, that's the vertical displacement, so it's h equals x sine 30. Now let's think about the increase in kinetic energy. The increase in kinetic energy is half mv squared minus half mu squared. So that's half times 0.5 times 6 squared minus 0. So that works out to be 9 joules. So the conservation of mechanical energy says that the total energy remains fixed. In other words, the increase in kinetic energy must equal the decrease in potential energy. So in other words, 9 equals 0.5 g x sine 30. If you solve that equation, x works out to be 3.7 meters to 2 sig figs. So this conservation of mechanical energy is something that applies when there's no external forces other than gravity. The next example we'll see where it becomes a little bit more complex. So in this example we've got a mass 2 kilograms projected up a slope with speed, initial speed equal to 8 meters per second. The slope's inclined at 45 degrees and the coefficient of friction is 0.4. We can use the work-energy principle, which is that the work done on a particle is equal to the change in the total energy of a particle. We can use this to calculate the distance the particle travels up the plane before coming to instantaneous rest. Now this is different to the previous example because the previous example there were no external forces, but in this case we have got an external force which is friction, which is acting down the slope. We've got a normal reaction, but as before, because the normal reaction is at right angles to the direction of motion, the normal reaction does no work, but there obviously is work done against friction. So using the work-energy principle, what we need to do is to find the change in the total energy of the particle first of all. So as the particle moves up the slope, it loses kinetic energy because it's slowing down, but it gains potential energy. So the total loss is the kinetic energy lost, but because it gains some potential energy, we need to take that away. So initially it had some kinetic energy, so half m8 squared, and by the end it had no kinetic energy, so that's half times 2 times 0 squared. So this is the amount of kinetic energy that was lost, and then the potential energy gained, that's m, g, and then it gains some by going a certain height. Now we don't know what the distance is here, that's how far it goes before the speed gets down to 0, but as in the previous example we can do a little right angled triangle like that. This is 45, so the height here is x sine 45. So that's the loss of energy. What about the work done? Well, the work done is the force multiplied by the distance, x in this case. So what is the force? Well, the force is frictional force, and as the particle moves up the slope, it's working against that frictional force. So how do we work out frictional force? We have to use F equals mu times R. What's R? Well, we need to resolve that 2g in this direction, so this is 2g cos 45. So it's 0.4 times 2g cos 45. So this then becomes 0.4 times 2, that's 0.8 g cos 45 multiplied by x. Now, we know that the work done is equal to the change in the total energy. So this number here must equal this here. So if I can squeeze this in, work done equals change in total energy, which means that equals this, and then from that solve that equation, and x works out to be 3.3 meters to 2 sig figs. Probably a good idea if you're going to set this out not to squash it in like I have, but to actually write down that equals that and then solve the equation. You'll find it's 3.3. And finally, we've looked at work, we've looked at energy. What about power? Well, the simple formula is that power is force times velocity. So if we've got a situation where we've got a truck being pulled up a slope at a constant speed of 8 meters per second, then the power developed by the truck is equal to force times the constant speed, which is 160,000, and the units are watts. Sometimes we consider kilowatts, where 1 kilowatt is 1,000 watts. And that's it, that's work, energy and power, and loads more examples to come in lessons.